Astronomers just detected something impossible. An asteroid nearly half a mile wide is spinning so fast it completes one full rotation in less than 2 minutes. That's faster than any large asteroid ever discovered. And according to every physics model we have, it should have torn itself apart millions of years ago. Right now, Asteroid 2025 MN45 is rotating at velocities that exceed the tensile strength of normal rocky material. At 710 meters in diameter, this is not a small pebble held together by its own negligible gravity. This is a mountain-sized object experiencing centrifugal forces that should rip it to pieces. And it's been spinning like this for potentially billions of years. The rotation period is precisely 102.2 seconds. That's 1 minute and 42 seconds per complete revolution. At the asteroid's equator, surface material is moving at approximately 21.8 meters per second, or 78 kilometers per hour, experiencing centrifugal acceleration that nearly cancels out the asteroid's weak surface gravity. The Vera C. Rubin Observatory detected this object in early commissioning data using the Legacy Survey of Space and Time camera, the most powerful astronomical camera ever built with 3.2 billion pixels. Dr. Sarah Greenstreet, assistant astronomer at NORLab, stated in January 2026, "This asteroid must be made of material that has very high strength in order to keep it in one piece as it spins so rapidly." Even more disturbing, this isn't an isolated case. The Rubin Observatory discovered 18 other large, fast-rotating asteroids in the same dataset, suggesting these objects are far more common than we thought. Asteroid 2025 MN45 broke the record for fastest spinning asteroid larger than 500 meters in diameter. Here's what should concern you most. If this asteroid is solid rock rather than a loose rubble pile, it means our fundamental understanding of asteroid formation and evolution is incomplete. And there may be thousands more of these physics-defying objects in our solar system that we simply haven't detected yet. Think about it. Before we dive deeper into this cosmic mystery, if you want to stay updated on what could be the most important discovery about asteroid physics this decade, don't forget to click the subscribe button and turn on notifications, because what we're about to reveal will completely change how you understand the rocks floating through our solar system. And leave a comment telling us, what do you think keeps this asteroid from flying apart? Let's talk about what asteroids actually are, because understanding their structure makes this discovery even more shocking. For most of the 20th century, astronomers assumed asteroids were solid rocks, fragments left over from the formation of the solar system, essentially miniature planets made of stone or metal. That picture changed dramatically in the 1990s and 2000s, as spacecraft visited asteroids and detailed radar observations became possible. What scientists discovered was that most asteroids aren't solid rocks at all. They're rubble piles, loose collections of boulders, gravel, and dust, held together by weak gravity and minimal internal cohesion. The asteroid Itokawa, visited by Japan's Hayabusa spacecraft in 2005, exemplified this. High-resolution images showed the surface covered in boulders of varying sizes with virtually no fine dust. The entire asteroid appeared to be a gravitationally bound collection of fragments, probably the result of a catastrophic collision that shattered a larger parent body millions of years ago. Similarly, the asteroid Bennu, studied extensively by NASA's OSIRIS-REx mission from 2018 to 2021, showed clear evidence of being a rubble pile. Its extremely low density, only slightly denser than water, indicated the interior must be highly porous, filled with voids between loosely packed fragments. This rubble pile structure has important implications for asteroid rotation. Because the components aren't rigidly connected, there's a maximum rotation speed beyond which centrifugal force overcomes the weak gravity holding the pile together. The asteroid essentially flies apart, scattering fragments into space. That maximum rotation speed is called the spin barrier, and for decades it's been well established observationally. Asteroids larger than about 200 meters in diameter almost never have rotation periods shorter than about 2.2 hours. That's the spin barrier. Below 200 meters in diameter, asteroids can spin faster because small objects have higher tensile strength relative to their size. A 10-meter boulder can spin very rapidly without breaking apart because molecular forces holding the rock together are sufficient. But large asteroids, objects hundreds of meters to kilometers in diameter, can't spin that fast, or so we thought. Asteroid 2025 MN45 obliterates that assumption. At 710 meters in diameter, it's well above the size threshold where rubble pile structure should dominate. Yet it's spinning with a period of 102 seconds, far below the 2.2-hour spin barrier. The discovery was made by the Vera Rubin Observatory, located on Cerro Pachon in Chile, at an altitude of 2,715 meters. The observatory houses what is arguably the most powerful astronomical survey instrument ever built, the LSST camera. LSST stands for Legacy Survey of Space and Time, and the camera is a marvel of engineering. It contains 3.2 billion pixels arranged in 189 individual sensors, creating a focal plane about 64 centimeters across. The camera weighs approximately 3 metric tons and is cooled to 100 degrees Celsius to reduce thermal noise. The camera is mounted on an 8.4-meter telescope with a uniquely wide field of view, 9.6 square degrees, which is about 40 times the area of the full moon. This combination of large aperture and wide field makes the Rubin Observatory ideal for surveying the entire visible sky repeatedly, detecting transient events and moving objects like asteroids. The observatory is currently in its commissioning phase, the period where engineers and astronomers test the systems and verify everything works correctly before beginning the full 10-year survey. Even during commissioning, the camera is producing scientifically valuable data. In early January 2026, the team analyzing commissioning data noticed something unusual. They were looking at light curves, graphs showing how the brightness of asteroids changes over time as they rotate. As an asteroid spins, different parts of its surface reflect more or less sunlight depending on their orientation relative to the observer and the sun. This creates a periodic brightness variation that reveals the rotation period. Most asteroids show light curves with periods of several hours. Some spin faster, with periods of a few hours. But asteroid 2025 MN45 showed a light curve with a period of just 102.2 seconds. At first, the team suspected an error. Perhaps the data reduction pipeline had made a mistake. Perhaps they were seeing an aliased signal, a false periodic pattern created by the way the data was sampled. They checked the raw data. They reprocessed the observations with different algorithms. They examined the light curve in excruciating detail. The 102-second period was real. Dr. Greenstreet's team immediately recognized the significance. This wasn't just another fast-rotating asteroid. At 710 meters in diameter, this object was far larger than any other asteroid known to spin this quickly. They calculated the surface velocity at the asteroid's equator. For a spherical object with a 7 to 10 meter diameter rotating once every 102 seconds, points on the equator move at approximately 21.8 meters per second, or about 78 kilometers per hour. That might not sound extremely fast. It's about highway speed for a car, but for an asteroid, it's extraordinarily rapid. And here's why that creates a physics problem. Centrifugal acceleration at the equator can be calculated using the formula A.ev2r, where v is the velocity and r is the radius. For this asteroid, the centrifugal acceleration is approximately 0.31 meters per second squared. Now compare that to the asteroid's surface gravity. For a rocky asteroid with density around 2,500 kilograms per cubic meter and a radius of 355 meters, surface gravity is only about 0.027 meters per second squared. The centrifugal acceleration is more than 10 times stronger than the surface gravity. That means if you were standing on the asteroid's equator, you'd be flung into space. The centrifugal force trying to throw you outward is far stronger than the gravitational force pulling you down. For the asteroid itself, this creates enormous stress. If it's a rubble pile, a collection of loosely bound fragments, the centrifugal force should overcome the weak gravitational binding, and the asteroid should simply disintegrate, scattering boulders into orbits around the sun. The fact that 2025 MN45 hasn't disintegrated means it can't be a normal rubble pile. It must have internal cohesion, forces beyond gravity holding it together. Dr. Greenstreet's statement in the press release was carefully worded but significant. This asteroid must be made of material that has very high strength in order to keep it in one piece as it spins so rapidly. High strength means the asteroid is likely a monolith, a single coherent piece of rock, not a rubble pile. The material has sufficient tensile strength that even though centrifugal forces exceed surface gravity, the rock's internal molecular bonds prevent it from flying apart. But here's where it gets really strange. Monolithic asteroids are thought to be rare among large asteroids. Most asteroids this size have experienced collisions over billions of years that should have shattered them into rubble piles. For 2025 MN45 to be a monolith, it either formed recently, perhaps as a fragment from a larger body that broke apart within the last few million years, or it's made of unusually strong material, possibly metallic rather than rocky. Some asteroids are known to be metallic, fragments of the iron-nickel cores of differentiated planetesimals that broke apart early in solar system history. The asteroid Psyche, target of NASA's Psyche mission currently en route, is thought to be largely metallic. Metal has far higher tensile strength than rock. Could 2025 MN45 be metallic? The team doesn't have spectroscopic data yet to determine composition, but it's a possibility. And here's where the discovery becomes even more remarkable. Asteroid 2025 MN45 isn't alone. The Rubin Observatory team found 18 additional large asteroids with rotation periods shorter than expected for rubble piles. These objects range in size from about 500 meters to over 1 kilometer in diameter, and all are spinning faster than the spin barrier predicts. That's 19 objects total that violate the standard model of asteroid rotation. And this was found in just a tiny fraction of the Rubin Observatory's survey data collected during commissioning, before the full survey even begins. The full legacy survey of space and time is expected to begin in mid-2026 and will run for 10 years. During that time, the observatory will image the entire visible sky repeatedly, discovering millions of asteroids and tracking their properties. If 19 fast-rotating large asteroids were found in the commissioning data, how many will be found in the full survey? Hundreds? Thousands? Dr. Regina Rameka, Associate Director for High Energy Physics at the U.S. Department of Energy, commented in the press release. Discoveries like this exceptionally fast-rotating asteroid are a direct result of the observatory's unique capability to provide high-resolution, time-domain astronomical data, pushing the boundaries of what was previously observable. Time-domain astronomy, the study of how astronomical objects change over time, is one of the Rubin Observatory's primary science goals. By repeatedly imaging the same regions of sky, astronomers can detect transient events like supernovae, variable stars, and the changing brightness of rotating asteroids. But the implications of finding numerous fast-rotating large asteroids extend beyond just correcting our models of asteroid structure. These objects may represent a previously unrecognized population of asteroids with distinct formation histories. Perhaps they're young fragments from recent collisional disruptions that haven't had time to be spun down by tidal interactions or collisions with smaller objects. Or perhaps they're remnants of a different formation process entirely, objects that never went through the collision and reaccumulation cycle that creates rubble piles. Understanding these objects is important for planetary defense. If an asteroid were on a collision course with Earth, we'd want to know its internal structure to design an effective deflection strategy. A monolithic asteroid responds differently to impact or explosion than a rubble pile does. A rubble pile might absorb an impact, with the energy dissipating through the shifting of individual fragments. A monolith would respond more like a solid body, with the energy propagating through the structure as seismic waves. NASA's DART mission in 2022 demonstrated kinetic impactor technology by deliberately crashing a spacecraft into the asteroid Dimorphos, changing its orbit. But Dimorphos is likely a rubble pile. Would the same technique work as well on a monolithic fast rotator like 2025 MN45? These are practical questions with real implications for future planetary defense efforts. But there's another aspect of this discovery that's generating discussion among asteroid scientists. The spin rate of an asteroid isn't static. It can change over time due to a phenomenon called the Yorp effect, named after the scientists Yarkovsky, O'Keefe, Radzievsky, and Paddock, who contributed to the theory. The Yorp effect works through the absorption and re-emission of sunlight. When sunlight hits an asteroid, the surface absorbs the energy and heats up. Later, that energy is radiated away as infrared light. Because the asteroid is rotating and has an irregular shape, the emitted radiation isn't symmetric. The imbalance creates a tiny torque that can speed up or slow down the asteroid's rotation over millions of years. For small asteroids, the Yorp effect is strong enough to spin them up to very high rotation rates, sometimes fast enough that they shed material from their equators, creating binary asteroids or satellite systems. Could the Yorp effect have spun up 2025 MN45? Possibly, but there's a problem. The Yorp effect is stronger for smaller asteroids and weaker for larger ones, because it scales inversely with size. For an asteroid 7-10 meters in diameter, the timescale for significant Yorp spin-up is on the order of millions to tens of millions of years. If 2025 MN45 has been spinning this fast for tens of millions of years, it's survived an extraordinarily long time without disintegrating. That requires very high internal strength. Alternatively, maybe it's younger than we think. a recent fragment from a collision spun up rapidly by the energetics of the impact event that created it. The Rubin Observatory data doesn't yet provide enough information to distinguish between these scenarios. Follow-up observations, spectroscopy to determine composition, radar observations to map the shape, long-term monitoring to detect any changes in rotation rate will be needed. But here's what makes this discovery particularly exciting for the astronomical community. The Rubin Observatory hasn't even begun its full survey yet, and it's already making discoveries that challenge our understanding of asteroids. The LSST camera first light, the moment when it captured its first astronomical images, occurred in May 2024. Since then, the observatory has been in commissioning, testing systems, refining calibrations, and collecting engineering data. The full legacy survey of space and time is scheduled to begin in mid-2026. Over the subsequent 10 years, the observatory will image the entire visible sky roughly every few nights, creating a time-lapse movie of the universe. The survey will discover an estimated 10 million asteroids, more than doubling the current number of known asteroids. It will detect thousands of supernovae, millions of variable stars, and countless other transient events. And if the commissioning data is any indication, the full survey will reveal populations of objects we didn't know existed. The fast-rotating large asteroids are just the beginning, but here's where it gets unsettling. If our models of asteroid structure and rotation are this far off, if there are entire populations of objects that don't behave the way we predicted, what else are we wrong about? Asteroids have been studied for over 200 years since the first one, Ceres, was discovered in 1801. We've sent spacecraft to visit them. We've mapped their orbits. We've analyzed their compositions. We thought we understood them reasonably well. But 2025 MN45 suggests there are surprises still hiding in the asteroid belt and among near-Earth objects. Objects that violate the rules we thought governed their behavior. And here's the broader implication. Asteroids are the leftover building blocks of planet formation. They're samples of the primordial material from which Earth and the other planets formed 4.5 billion years ago. Understanding asteroids means understanding planet formation. If there are populations of asteroids with properties we didn't predict, monolithic fast rotators perhaps, it suggests there are aspects of the planet formation process we don't fully understand. Maybe collisional evolution in the early solar system was different than we modeled. Maybe there are formation pathways that produce strong monoliths instead of weak rubble piles. Maybe the distribution of material strengths in the primordial asteroid population was different than we assumed. These are fundamental questions about the solar system's history. Now, let's put it all together. An asteroid 710 meters in diameter is spinning once every 102 seconds, far faster than the spin barrier predicts for rubble pile asteroids. Centrifugal forces at its equator exceed surface gravity by a factor of 10, yet the asteroid remains intact. This indicates it's a monolith with high internal strength, possibly metallic composition. And it's not alone. 18 other large, fast-rotating asteroids were discovered in the same dataset. The probability of finding these objects before the Rubin Observatory, before we had a survey instrument powerful enough to detect them in large numbers, was essentially zero. We got lucky. We're not saying all asteroids are monoliths. Most large asteroids are still likely rubble piles. But the existence of a population of fast-rotating large asteroids means our simple models are incomplete. We've reached a point where even conservative planetary scientists are acknowledging that asteroid populations are more diverse and complex than we thought. The Vera Rubin Observatory is still in commissioning and hasn't begun its full survey. When the 10-year legacy survey of space and time begins in mid-2026, we expect to discover hundreds or thousands more of these objects. And here's what this really means. Asteroids aren't the simple, well-understood objects we thought they were. There are populations of asteroids with properties that challenge our models, and understanding them will require rethinking aspects of solar system formation and evolution. Studying asteroid 2025 MN45 and its fast-rotating cousins isn't just about correcting a model, it's about understanding what processes in the early solar system could produce mountain-sized monoliths that have survived billions of years of collisional evolution. So, what do we know for certain? First, asteroid 2025 MN45 has a confirmed rotation period of 102.2 seconds and a diameter of approximately 710 meters, making it the fastest spinning large asteroid ever discovered. Second, the centrifugal forces at its equator exceed surface gravity, which should tear apart a rubble pile, indicating it must be a monolith with high internal strength. Third, 18 other large, fast-rotating asteroids were discovered in the same Rubin Observatory commissioning data. What don't we know? What is the composition of 2025 MN45? Is it rocky or metallic? How did it achieve such a high rotation rate? Through Yorp's spin-up over millions of years or through a recent collision? And most importantly, how common are these objects? Will the full Rubin survey find hundreds, thousands, or more? And here's the urgency. The Vera C. Rubin Observatory is about to begin the most comprehensive sky survey in history. Over the next 10 years, it will discover and characterize millions of asteroids. The objects we discover will reshape our understanding of the solar system's formation and evolution. Because if follow-up spectroscopic and radar observations confirm that 2025 MN45 and similar objects are solid monoliths, we'll have identified a previously unknown population of asteroids that survived intact from the solar system's violent early history. The truth is this: there are asteroids spinning so fast they should have destroyed themselves millions of years ago, yet they're still intact. The forces trying to rip them apart are stronger than the gravity holding them together. And the only thing keeping them from flying into pieces is the internal strength of solid rock or metal. And the only way to understand how these objects formed and survived is through continued observations with the Rubin Observatory and follow-up studies with other telescopes before these fast rotators evolve or collide with other objects and change. If this video left you questioning how much we really understand about the rocks floating through our solar system, don't forget to click the like button and subscribe to this channel. We're tracking discoveries from the Vera C. Rubin Observatory in real time as it begins its full survey in 2026, and you won't want to miss what other physics-defying objects it finds. Leave a comment with your theory. Is asteroid 2025 MN45 made of solid metal, solid rock, or something else entirely? And share this video with anyone who thinks we've already discovered all the weird objects in the solar system. After watching this, they'll never think about asteroids as simple space rocks again. Some of them are spinning time bombs that physics says shouldn't exist.